This video is going to introduce photoelectron spectroscopy, explain briefly how it works, and show you what information we can gain from the spectra produced. But first, let's back up and review some history. After John Dalton published his atomic model in 1808, it was almost a full century before another scientist made any advance in the study of the atom. What evidence did J.J. Thomson have to support his idea of electrons and the plum pudding model? He had observed the behavior of gases in a cathode ray tube passing through a magnetic field. What then led Rutherford to revise Thomson's model to now include a dense central core? He saw alpha particles shot at a thin sheet of gold foil, sometimes bouncing off at crazy angles. What evidence exists to suggest that electrons have quantized energy levels in atoms? This is what Bohr predicted based on studying the atomic emission spectrum of hydrogen. The reason only specific bands of light are emitted by excited atoms is because the electron can only move between certain allowed energy levels. If the electron in the atoms could have any possible energy amount, then excited atoms should emit a continuous spectrum of all colors of visible light. Since we can see that doesn't happen, we know Bohr was right. The electron in an atom has only certain specific allowed energies. When an electron in an excited state moves from one specific level down to a lower level, the atom emits a photon of light of one specific energy, the energy equal to the difference between the two energy levels. This results in a distinct band of light in the emission spectrum. Ionization energy data also shows evidence for electrons existing in shells. Look at successive ionization energy values for elements. For every single element, the second ionization energy is always greater than the first. The first ionization energy refers to removing one electron from the neutral atom. The second ionization energy, then, is associated with removing an electron from an already positive ion. That second process will always require more energy than the first one. The more positively charged the ion, the harder it is to remove an additional electron. Additionally, we can see that for every element, at some point, the next ionization energy value increases tremendously. This is more evidence that electrons exist in shells. While the second ionization energy for magnesium is roughly double the first ionization energy, the third ionization energy is more than 5 times greater than the second. This third electron was much more tightly held by the nucleus, meaning it must have been significantly closer to the nucleus. The third electron removed from magnesium was in a lower shell. It was a core electron. The first 2 electrons were valence electrons. For any element, we can see the difference between valence electrons and core electrons looking at successive ionization energy values. Aluminum, for example, has 3 valence electrons because its large jump in ionization energy is at the 4th ionization energy. Phosphorus has 5 valence electrons. Its large jump is at the 6th ionization energy. Look at this graph of first ionization energy data for different elements. First ionization energy increases from hydrogen to helium. The value then drops way down at lithium and generally increases again through neon. The value drops again at sodium, then generally increases to argon. This trend suggests that the electrons are added to the same shell for a time, then a new shell of electrons is added. But the trend is not completely uniform. Notice that the first ionization energy drops from beryllium to boron. It does it again from nitrogen to oxygen. We see those same drops in the same place, second to third element, fifth to sixth element, in the next series. This variation to the overall general trend is evidence of subshells and orbitals. Schrödinger's wave equations mathematically describe subshells and orbitals, but this data shows proof of their existence. The additional electron in boron is added to a subshell that is, for various reasons, higher in energy than the subshell containing beryllium's electrons. As a result, boron's outermost electron is easier to remove than beryllium's. Boron's outermost electron is in a higher subshell, so it's a little less tightly held by the nucleus, so it has a lower ionization energy. So scientists know of and have quite a bit of evidence for the existence of electron shells, subshells, and orbitals. Scientists also know the relative energies of these shells and subshells, so we can easily and accurately predict electron configurations for most atoms. We know the general order of subshell filling: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on. But how can scientists experimentally confirm these electron configurations? And what about elements that don't follow the typical filling pattern? Chromium, molybdenum, copper. How do scientists know that these elements have electron configurations different from the general prediction? The answer is photoelectron spectroscopy. Photoelectron spectroscopy is based on the photoelectric effect. Shine a light of sufficient energy on a metal surface and electrons will be ejected. In photoelectron spectroscopy, scientists measure the kinetic energy of the ejected electrons. They also know the energy of the incoming light. It was specifically selected for the experiment. The difference between these two values is the energy needed to remove the electron. In other words, the ionization energy of the electron equals the energy of the photon of light used minus the kinetic energy of the ejected electron. To remove a valence electron, UV and sometimes visible light provides sufficient energy. But to remove a core electron, the incoming photons must have much higher energies, like in the X-ray range. The electrons in the first shell, the closest shell, are most tightly held by the nucleus. So electrons in the first shell will require the greatest amount of energy to remove. Understand that any photon of light with sufficient energy to remove an electron from the first shell can remove an electron from any shell. We use X-rays energetic enough to eject a core electron with some amount of kinetic energy. If those X-rays instead eject a second shell electron, the second shell electron will exit with more kinetic energy. I'll say that again. If specific energy photons eject a first shell electron, most of the energy is required for the ionization process. little energy remains to impart kinetic energy to the electron. If that same energy of photon ejects a second shell electron, less energy is required for the ionization process, so more of the energy becomes kinetic energy of the electron. What scientists do then in a PES machine is shine an X-ray source on the metal sample. The ejected electrons travel through a hemispheric kinetic energy analyzer. The outer and inner plates are both negatively charged, the inner plate slightly less so than the outer. This charge difference alters the path of the electron out of a straight line. If the kinetic energy of the ejected electron is too high, the electron will quickly crash into the top plate. Its trajectory was not bent enough for it to make the turn through the plates. If the kinetic energy of the electron is too low, it's pulled down and hits the bottom plate. So, scientists slowly adjust the charge on the two plates over time to measure the kinetic energy of all the ejected electrons and separate them by their amount of kinetic energy. That data is then graphed to create a photoelectron spectrum, which looks like this for a simple element like lithium. The x-axis is labeled energy. That's usually binding energy, a measure of how tightly an electron is held by the nucleus. You can think of it like ionization energy. How much energy does it take to remove that electron from the atom? Along the x-axis on this graph, we see two peaks, telling us that there are electrons of two different energies in a lithium atom. The y-axis is the relative number of electrons. That's not the same thing as if it were labeled just number of electrons. A peak height is only important relative to the other peak heights. The peak on the left is twice the height of the right-hand peak, indicating twice as many electrons at that energy than at the other energy. Take notice of two features of the x-axis. First, it is in descending order. I'll explain why in just a minute. Not so obvious is that the x-axis uses a log scale. That's why the peak labeled 6.26 megajoules per mole is much closer to 10 than it is to 1. Knowing this, we're seeing that lithium has twice as many electrons with an energy of 6.26 megajoules per mole as electrons with energy 0.52 megajoule per mole. Which electrons in an atom are most tightly bound? The ones in the first shell. They're the closest to the nucleus, so they're the most tightly bound. The higher energy peak, the one on the left, represents these first shell electrons. The reason the x-axis is often drawn in reverse order is so you can picture the nucleus sitting on the left edge of the graph, and you're reading outward from the nucleus as you read to the right. Let's look at the PES for another element to study more aspects of these graphs. Here's the photoelectric spectrum for the next element, beryllium. It's different from lithium's PES in two ways. Let's look at both graphs together to more easily compare them. The graph for lithium is in blue, that of beryllium is pink. We see that the second peak in beryllium is larger than the second peak of lithium. What does peak height represent? Peak height tells us about the number of electrons in that energy level. So we see beryllium has the same number of electrons in its first energy level and in its second level. We also see that the peak for each level is higher in energy. Remember, the x-axis is reversed in beryllium than the same energy level in lithium. Why does this happen? What else is different about beryllium than lithium? Think about the nucleus. Beryllium has one more proton in its nucleus, so its nucleus pulls harder on all its electrons than lithium's nucleus. So all the energy shells are higher in energy in beryllium. Here again is the spectrum for beryllium. How do you expect the spectrum for the next element, boron, to look different? We know the peaks will move left, representing higher energies, because boron's nucleus exerts a stronger pull than beryllium's. How will we see the additional electron? Here is boron's spectrum. Did you expect to still see two peaks, with the right-hand peak getting higher? But that's not what happened. Instead, we see a new peak added. What does that mean? It means we have electrons in now 3 different energy groupings. Still putting the nucleus on the left and reading to the right, what does the first peak represent? This peak represents the electrons in the 1s shell. The second peak is the 2s level, and the new peak represents an electron in the 2p level. In multi-electron atoms, sublevels within a principal energy level have different energies due to nuclear shielding and the spatial distribution of the electrons. So each sublevel will show as a separate peak on a photoelectron spectrum. There's a much greater gap between the first and second peaks than between the second and third peaks. Peaks spaced far apart are in different principal energy levels. There's a substantial difference in their energies. Peaks that are rather close together are sublevels within a principal level. Their energies are definitely different, but much closer to each other than to other principal energy levels. So do peaks on a PES represent principal energy levels or sublevels? Each peak represents a different sublevel. And what do the peak heights tell us? That's the relative number of electrons at that energy. Let's do one more prediction. What will the PES of the next element, carbon, look like compared to borons? All peaks are shifted left to higher energies because of the stronger nuclear pull. The rightmost peak is taller, equal in size to the other two. All these energy levels contain the same number of electrons. Look at the complete photoelectric spectrum shown. Identify the element and write its electron configuration. Starting on the left, the first peak represents the highest energy electrons. Those are the electrons in the 1s level. We know that contains 2 electrons. The next peak is the 2s level, holding the same number of electrons as 1s. The next peak is 3 times higher, so it contains 3 times more electrons. This is the 2p level, holding 6 electrons. Continuing on, the next peak represents 3s, holding 2 electrons. Then the rightmost peak represents the next sublevel, which is 3p. How many electrons are represented by that peak? Compare this peak height to the others. On this particular graph, we can see that each line up the y-axis refers to one electron. So the 3p level in this element holds 3 electrons. What element is represented by this electron configuration? That would be phosphorus. Here's the question asking you to compare one specific peak from the lithium and beryllium spectra. Notice that it does not show you complete spectra, only the peaks referred to in the question. Which of the following best explains the relative positioning and intensity of the 2s peaks in the following spectra? In other words, why is the beryllium 2s peak to the left higher in energy than the lithium 2s peak? And why is the beryllium peak taller than the lithium peak? Intensity refers to peak height. The correct answer is A. Because beryllium has a greater nuclear charge, all the peaks in its spectrum would be higher in energy to the left of the equivalent peaks in the lithium spectrum. Peak height is based on the number of electrons at that energy. A higher peak in beryllium tells us that there's more electrons in that level than in lithium. Notice, choice B is actually a correct statement. Beryllium electrons do experience greater electron-electron repulsions. But that statement doesn't explain the positioning and intensity of the two peaks in question. When given a photoelectron spectrum, read the question. See what information is given on the graph. This question says you are given spectra for sodium and potassium. One graph showing you one peak for sodium and one peak for potassium. The question is, what explains the difference in binding energy for their 3s electrons? Remember, binding energy can be thought of the same way as ionization energy. Why does the potassium peak show up at a much higher energy than the sodium peak? Choices A, B, and C are all true statements, but which one explains the difference in binding energy? The position of the peaks is based primarily on the strength of the nucleus, so A is the correct answer. Here's the link to a website where you can generate photoelectric spectra for the first 21 elements. You can click on any element in the abbreviated periodic table at the top. These spectra look different from the ones we've been looking at. One, the x-axis is not reversed. So remember that the highest energy peak is always the electrons closest to the nucleus. Also, this is one spectrum split onto two lines, 0 to 10 on the bottom line, continuing 10 to 100 on the next line. This is the spectrum for fluorine. Its highest energy peak at 67.2 megajoules per mole represents the 1s level. The next highest energy peak at 3.88 megajoules per mole is the 2s level. The lowest energy peak at 1.68 megajoules per mole is the 2p level. On this website, you can also compare multiple spectra by choosing the dual mode at the top. Pick an element for the left side. Click the right side radio button and choose a second element to display on the right. You can then compare their spectra side by side. Sodium and magnesium here, for example. We can compare peak positions and peak heights. For example, we can see that all the peaks in magnesium have higher energies than the comparable peak in sodium. We can see that the lowest energy peak of magnesium is twice as big as the lowest energy peak in sodium. Quick summary. Photoelectron spectroscopy is one method for confirming electron configurations for elements. This is especially useful for studying elements with anomalous electron configurations. Photoelectron spectroscopy is based on the photoelectric effect. Shine high-energy light onto a sample and measure the kinetic energy of the ejected electrons. A photon of light transfers its energy to an electron, ionizing the electron and giving it some kinetic energy. Knowing the energy of the photons used and measuring the kinetic energy of the ejected electrons allows us to determine the ionization energy or binding energy of each electron in an atom.